For this problem, what we want to do is, given a mass spring system, we want to determine the spring constant K, and then we want to find the initial value problem for two different scenarios. First part, what we want to do is find K. What we have here is a mass spring system, which means if we have a spring like that, and then a mass hanging off of it, so 1 kilogram mass. The forces acting on this mass, there's a spring force pulling it upwards, so we'll call that Kx. And then there's a gravity force pulling it downwards, which is mg. Where our x is our displacement, and g is our gravity, m is our mass, and k is our spring constant. Since this object naturally stretches the spring 5 centimeters, so if you just let this object rest on the spring, then the spring stretches 5 centimeters. So it's at rest, it's not moving, there's no other forces acting on it. So we know that Kx should be equal to mg, since all the forces are balanced. And what we get here, solving for K, is we get mg over x. So our m is 1 kilogram, our g is 9.8, and then our x is 5 centimeters. So if you write that in meters, it's 0.05 meters. And the reason we want to convert it to meters is because our 9.8 value is in meters per second squared. So we want to have all the units line up here. So we get our K value. If we work this out, we get okay, so for the second part, what we want to do is we want to set up another initial value problem. So if the mass is displaced 5 more centimeters and then released, then the mass will be oscillating. It will go up, down, up, down. And we want to write a differential equation that describes that motion. So the way we would do that, first of all, what kind of oscillation are we looking at? We're looking at first it's unforced, which means that there's no other external force causing it to go up and down. It is just a spring and gravity. And it's also undamped, because we weren't given any information about any dampening force, about anything that will obstruct the free-flowing harmonic motion. So if it's unforced and undamped, the kind of differential equation we would get, something of this form. The most general form of this equation is where this is our damping constant, so our spring constant, and then this is our forcing function. Here we have no dampening, so this is 0, and we have no forcing, so this is also 0. So we get this equation here on the left. We know what m is 1 kilogram, and we know what k is 196. So just plugging in values. And we also can't forget about our initial values, since this is an initial value problem. So y0, yt here represents a displacement, or a distance that the spring is stretched past its equilibrium. We know from part 1, the 1 kilogram mass automatically stretches the spring 5 centimeters. So its resting position is at 5 centimeters. And then in part B, we pull it 5 centimeters more. So our extra displacement here, y0, is 0.05, because at the start of our motion, we have physically stretched the mass an additional 5 centimeters, and then we released it. So y0, which is our initial distance or displacement, is 0.05. Y prime 0, that's our initial velocity in meters per second. Well, when we release the mass, it is at rest, right? We don't push it up or push it down. So we can assume that our initial velocity is 0. And this becomes our initial value problem. Okay, so that's part B. And now for part C, we have a damping fluid, so a fluid that exerts a damping force of 0.25 kilograms when the mass is moving at 2 centimeters per second. So let's write that down here. We have one thing about our damping force, if you can see that it's in a fluid, and we assume that damping is proportional to the velocity of the object. We have velocity as the first derivative of position, so y prime t. And this is the velocity at time t. And what we have here, our damping force, is that when this value is 2 over 100, then our force is 1/4 of a kilogram. So what that means is that 1/4 of a kilogram is equal to our damping constant times our velocity. So then solving, we get our damping constant. So now that we have this, we can go back up to our general form here and just plug in for this middle term. Still, for part C, it's still unforced because there's no external forcing function here. So this right side is still 0, but our general equation is of this form. So plugging in, what we get here is, and we still have the same initial values. Our initial displacement is 5 centimeters, 0.05 meters, and then our initial velocity is still 0 because we're letting go of this mass when it's at rest.